So I'll actually start this next segment of the class by reading you a story. And I mean that quite literally. So now is a good time to pause and get yourself a glass of milk and a cookie if you feel so inclined. So here's the story I wanted to read you. It's by David McIntyre, and it's from the prologue to Quantum Mechanics: A Paradigm's Approach, which is the text that is usually used in Physics 421. It was a dark and stormy night. Irwin huddled under his covers as he had done numerous times that summer. As the wind and rain lashed at the window, he feared having to retreat to the storm cellar once again. The residents of Irwin's apartment building sought shelter whenever there were threats of tornadoes in the area. While it was safe down there, Irwin feared the ridicule he would face once again from the other schoolboys. In the rush to the cellar, Irwin seemed to always end up with a random pair of socks, and the other boys teased him about it mercilessly. Not that Irwin hadn't tried hard to solve this problem. He had a very simple collection of socks, black or white, for either school or play, short or long, for either trousers or lederhosen. After the first few teasing episodes from the other boys, Irwin had sorted his socks into two separate drawers. He placed all the black socks in one drawer and all the white socks in another drawer. Irwin figured he could determine an individual sock's length in the dark of night simply by feeling it, but he had to have them pre-sorted into white and black because the apartment generally lost power before the call to the shelter. Unfortunately, Irwin found that this pre-sorting of the socks by color was ineffective. Whenever he reached into the white sock drawer and chose two long socks or two short socks, there was a 50% probability of any one sock being black or white. The results from the black drawer were the same. The socks seemed to have forgotten the color that Irwin had determined previously. Irwin also tried sorting the socks into two drawers based upon their length, without regard to color. When he chose black or white socks from these long and short drawers, the socks had also forgotten whether they were long or short. After these fruitless attempts to solve his problem through experiments, Irwin decided to save himself the fashion embarrassment, and he replaced his sock collection with a set of medium-length brown socks. However, he continued to ponder the mysteries of the socks throughout his childhood. After many years of daydreaming about the mystery socks, Erwin Schrödinger proposed his theory of quantum socks and became famous. And that is the beginning of the story of the quantum socks. The end. Far-fetched? You bet. But Irwin's adventure with his socks is the way that quantum mechanics works. Read on. That story about Irwin and his socks actually has a lot to do with Stern-Gerlach experiments. Let me now go to a PhET where I'll show you that and how we can get a situation that's exactly analogous to the sock situation. So I wanted to show you this simulation of the Stern-Gerlach experiment. The idea is that we have sort of atoms that we fire out here. Here's our Stern-Gerlach device, and it's oriented vertically right now. And so if I fire an atom, it comes out and then into the device, and then depending on whether it's spin up or spin down, and let's assume Z is vertical here, it either comes out or gets blocked by this paddle here. I can change sort of the paddle position if I click that. But the point is, right, so this is sort of random what happens. I'll either get the atoms being blocked or coming out, and over time if I build this up, I'll build some statistics. I can turn on this auto fire thing here where it's just shooting up a beam. And I think you can see that with just one device, we have 50% of my atoms being spin up and the other half being spin down. Okay, so let's now I'll stop this. Let's now consider a situation where we have two Stern-Gerlach devices. So let me start by keeping this also in the same orientation. And what the way this is set up, the output of this is going to get shot into this device. So let's turn on the beam again. So not surprisingly, nothing changed here. About half of the beam is coming through with spin up, while the other half is being blocked. But then subsequently, every atom that came out spin up here, if we measure the z component of the spin again, it's still spin up. Okay, so now let's imagine rotating this. So let's change this second device to be horizontal. So 90. So now we're measuring the x component of the electron spin. We're taking all of the spin up atoms that came out from here and feeding them into this Stern-Gerlach X device. Let's see what happens. So if we turn this on, so notice we have all spin up coming here, but then this output, well, half of them have Sx equals positive h bar over 2, and about half of them have Sx down, equals minus h bar over 2. Okay, so states of sort of definite Sc, we seem to not be able to tell what, predict what we'll get if we measure Sx. So I'll just convince you that, whoops, let me convince you that this really is random, and we cannot predict what comes out over here. Okay, so the really wacky thing happens if we now add a third Stern-Gerlach device. I'll keep this one oriented along z. So we have z, x, and z. Let's see what happens when we turn the beam on here. Surprisingly, right, out of this third Stern-Gerlach device, about half of my atoms are spin up and the other half are spin down. But we started with all spin up atoms at the output of this guy when it fed into this horizontal Stern-Gerlach device. So what's going on here? Now, if it's not apparent, this is what the story by McIntyre was talking about in relation to Irwin's socks, right? So Sz corresponds to one of the two properties. So in the story, he originally sorted the socks by color. So like Sz here might correspond to the socks being black or white. And then Sx being up or down is analogous to the socks being long or short. So this is like, we sort the socks with this device. So we have all of our socks of one color. So let's say all of our black socks here, and then we try to take two let's say long socks, so that'd be like taking the socks from here. But instead of those socks still being all black, right, we now have 50% probability of getting a black sock or a white sock. So this is one of the coolest things about quantum mechanics, and we'll go back to the whiteboard and I'll give you a short explanation for why. So I've tried to sketch on the board sort of a schematic representation of what I showed you in the PhET simulation. So I'm going to just call a Stern-Gerlach device, I'm going to just label that SG. So this box I'm going to draw to represent a Stern-Gerlach device that has a magnetic field gradient pointing in the z direction. So that's like the first device we had. So we've got some beam of atoms going into here, and then the output of the Stern-Gerlach, right, is we can have the spin up atoms that are come out on deflected one way, and the spin down ones deflected the other way. I'll sort of just schematically draw this as like a box with two possible outputs, so plus or minus. And we imagine that we sort of collect one of the outputs but block the other one, like in the simulation. We then send the beam that came out here through a Stern-Gerlach device that has a field gradient in the x direction. So that's that SGX here. So we then take the beam that has a spin component in the positive x direction and send that through another Stern-Gerlach Z device. And as we saw in the simulation, and as in the story of the long and short versus white and black socks, we get 50-50 coming out here. So this is totally weird, right? Because we know that everything that went in here, all of these had SC equals h bar over 2, or these were spin up, right? Then what on earth happened between here and here to give us half of them at the end spin up and the other half spin down? Well, the answer has to do with measurement and the principles of quantum mechanics that we talked about a bunch of classes ago. So the Stern-Gerlach Z device, sort of mathematically, you can think of its action as it applies that SZ operator we talked about as a 2x2 matrix. Remember that the outcome of a quantum measurement can only be one of the eigenstates of the associated operator. So all of the atoms that come out here, these are all eigenstates with spin up. So the spinner that describes this is chi plus that we talked about. But then the same thing happens here, right? When we have the Stern-Gerlach X device, the outcome of measuring spin, the x component of the spin, can only be one of the eigenvectors of the Sx operator. So the state here, I haven't defined a notation for it. Let me just call it chi x plus to denote it is x and positive. This has got to be an eigenvector of Sx operator. The reason for this funky behavior is that it turns out that the spinner, this one over here, is a superposition of the two possible SZ eigenstates. Namely, right, so 1 over root 2 chi plus 1 over root 2 chi minus, or if I wanted to think about the spinner explicitly as a column vector, I would get 1 over root 2 times 1, 0, or plus 1 over root 2, 0, 1, which is 1 over root 2, 1, 1, by just thinking about how I add vectors and matrices. But the key takeaway, right, is the following. Notice it's just like what we talked about with, like, the infinite square well or harmonic oscillator, right? We've written this sort of state here as a sum of the eigenstates of Sz, right? The coefficient in front here turns out to be related to the probability of measuring that, measuring my spin being up. So the probability of spin up spin Sz equals h bar over 2 turns out to be this coefficient, modulus squared, or 1/2. So it's the same sort of formalism as we talked about before. Same thing over here. The probability for measuring SC equals minus h bar over 2 is also 1/2. It is because, right, this here is in a superposition of the two SC eigenstates that we have this phenomenon. This also really drives home the fact that measurements in quantum mechanics, right, that the idea of collapse, measurement inherently changes the quantum state of what you are measuring. So namely, the quantum state coming in here is not the same as the quantum state coming out here. So that was I know that was a little bit of a lightning tour, but think of this as a preview of things to come in 421, which I hope you take.